The last time that we worked with exponential equations, we were working with exponential equations that had common bases. So we were able to create common bases on each side of the equation, drop the bases, set the exponents equal to each other, and solve the equation. However, we have problem number 1 here, 3 to the x power equals 81. And there is no base that we can use that would allow us to make this equation have common bases. We can't manipulate it to get that result. So instead, we're going to utilize the ability to convert back and forth between exponential and logarithmic equations. So we are going to convert this exponential equation into a logarithmic equation. So we'll have log base 3 of 80 equals x. And at this point, you'll see that we're able to just type that into our calculators, and it will give us our solution of x equals 3.9887. We typically round logarithms to 4 decimal places in this class. And then when we get our solution, we will always want to plug it back in to check our answer, but also to identify any extraneous solutions. In this case, 3.9887 is a true solution, so we're able to accept that and be finished with the problem. Now, as always, we're going to build on the easiest version of the problem. So that was a very simple problem. Now we're going to do one that's just a little bit harder. This one first requires us to isolate the exponential expression. So the exponential part is the exponent and whatever it's attached to. So 4 to the 2x plus 7. We want to isolate that. We'll start by subtracting 9 from both sides. And we get negative 2 times 4 to the 2x plus 7 equals negative 64. And then we'll divide both sides by negative 2. And we get 4 to the 2x plus 7 power equals 32. Now I am noticing that 4 and 32 actually have a common base of 2. And therefore we could go back to our old method here. But for the sake of teaching this method, we're obviously not going to take that route today. We're going to go ahead and convert this to a logarithm. We'll have log base 4 of 32 equals 2x plus 7. And then when you have logarithms involved in your equation, you're just going to keep that logarithm in one piece as it is and do all of the inverse operations to isolate x. And then at the end of our problem, we will plug whatever it is that we have into our calculator, and that way we're not rounding within the middle steps of our problems. So we're going to subtract 7, and we get log base 4 of 32 minus 7 equals 2x. Sometimes it's helpful here to put parentheses around the 32 to make sure that you emphasize the fact that the minus 7 comes after the logarithm and is not inside of it. So the next step we would take would be to divide both sides by 2. So we'll get log base 4 of 32 minus 7, all divided by 2 equals x. And then we're able to type this into our calculators, and our solution will be x equals negative 9/4, or you could write it as negative 2.25. Either way is acceptable. Then we always substitute our answer back in for x, make sure it works in the equation. That way we're checking for any extraneous solutions and also double checking our algebra. So this is a true solution to this equation. So we are finished with number 8. Now for number 9, we're going to use 2 different approaches. So I'm going to show you the same thing that we've been doing. We're going to convert to a logarithm and proceed from there. And then I'm going to show you a little bit different method. For a problem like this, where we have exponential expressions on both sides of the equation, we are just going to choose one to kind of be the primary exponential expression. So in this case, I chose the left side just to keep our standard conversions neater and keep them in the same order. So we're going to have log base 2 of 3 to the x minus 2 equals x plus 5. Then we know that the power property of logarithms says that we can bring this exponent out in front as a coefficient. So we have x minus 2 log base 2 of 3 equals x plus 5. Now, you're just going to have to trust the process with me a little bit on how to get this x isolated. So the first thing I'm going to do is distribute this logarithm through this binomial. So we have x log base 2 of 3 minus 2 log base 2 of 3 equals x plus 5. And then my x's are on opposite sides of the equation, so I want to move all the terms that have an x to one side and all the terms that don't have an x to the other side. So I'm going to end up with x log base 2 of 3 minus x equals 5 plus 2 log base 2 of 3. And now that my x's are on one side of the equation, I can factor that x out as a GCF. And that leaves me with log base 2 of 3 minus 1 equals 5 plus 2 log base 2 of 3. And then finally, to isolate x, I can divide both sides by this logarithm. And we will get x equals 5 plus 2 log base 2 of 3 over log base 2 of 3 minus 1, which is going to be tedious to type in your calculator, but it is the correct answer, and it will give us a solution of x equals 13.9666. And then, of course, I would plug that solution back into the equation and make sure that it works, and it does. All right, now I want to show you an alternate method because for some of these, it's a little bit cleaner. So what we can do is, instead of converting this to a logarithm, we can take the log of both sides. So we can just say that log of 2 to the x plus 5 equals log of 3 to the x minus 2. And then on both sides, we're going to bring our exponents down as coefficients. So we'll get x plus 5 times log 2 equals x minus 2 times log 3. Then we will distribute, similar to the last method, x log 2 plus 5 log 2 equals x log 3 minus 2 log 3. And then, again, similar to the last time, I want to bring everything with an x to one side and everything without an x to the other side. So we'll have x log 2 minus x log 3 equals negative 2 log 3 minus 5 log 2. Then we will factor x out and get log 2 minus log 3 equals negative 2 log 3 minus 5 log 2. And finally, we can divide. We will get x equals negative 2 log 3 minus 5 log 2 over log 2 minus log 3. And probably my favorite thing about this method is that my logs no longer have bases. So when we type this in our calculator, it will be easier to type in, and it requires about the same amount of work. But either way, we get the same solution, 13.9666, and now you have two methods for solving these more complex equations.